Good morning everyone. Myself Dr. Inderjit Kaur, Associate Professor in the Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. In this lecture, we will be studying about the Computer Organization and Architecture course. So, after covering the synchronous and asynchronous data transfer, in this lecture we will be doing the modes of data transfer. There are three modes of data transfer. One is programmed input output, interrupt initiated input output, and the third one is DMA, that stands for direct memory access. So, in this lecture we will be covering the first and second one, that is programmed input output and interrupt initiated input output. As we know that the information that is transferred from the CPU to the external device, it is originated from the memory unit. So, if the memory unit and IO device they wants to communicate, suppose we want to type anything from the keyboard and we want to save it into the any memory device. So, basically the memory device and the IO device they are communicating with each other with the help of CPU. So, in that case as these two devices they are different one and CPU is continuously monitoring them. So, in that case CPU is just wasting its CPU cycles, so it is not doing anything productive. So, for these kind of data transfer there are basically three modes of transfer, we will be studying that. So, the information that is transferred from the CPU to any external device using the memory that is originated from the memory unit, either it will be memory read or it will be memory write. So, the CPU it merely processes the information, but the source and the target they are the memory unit, as I told ki either we will be doing the memory read or we will be doing the memory write operation. So, the data transfer between the central computer to IO device it can be handled in three possible ways, and the possible ways are: one is the programmed IO, we have done some programming and through that program CPU is continuously monitoring, and the second one is interrupt initiated IO. In that case, if any device is interrupting, if any device it wants to communicate to the CPU, then it will send an interrupt to the CPU and corresponding action will be taken by the CPU. And the third one is direct memory access, that is DMA. In this, CPU will relinquish its control and through interface the devices and the memory they will be communicating. So, we will be studying first two modes in this lecture, and the DMA it will be covered in the next lecture. So, first is programmed IO. Programmed input output operations, they are the result of IO instructions, input output instructions like in, out, they are written in my computer program, and the data transfer from CPU or to CPU through external device or external device to CPU, whatever is sent, they are continuously being monitored by the CPU. Then this data transfer it is done by sending or writing the instruction programs, and that is being executed by the CPU and it is continuously monitored by the CPU. So, the transferring data under program it requires constant monitoring of the peripheral by the CPU. That is the first most task in this mode, that is in programmed IO. So, once the data transfer it is initiated, the CPU is required to continuous monitor the interface only to see when a data transfer can be made again for the second device or when the third device it requires to transfer the data. So, in this way CPU is continuously busy and it is not doing any productive task. So, let us take an example of programmed IO. Here this is my processor, this is our interface and this is the IO devices. As we have discussed in the previous lecture, all the input output devices they are communicating with the CPU through interface, because CPU is an electronic device and these IO devices they are either electromechanical or mechanical devices depending upon their function. So, first thing, the valid data will be sent by the IO device that it wants to communicate to the CPU, and accordingly it will place its content on the data bus. So, in the interface what will happen, as the valid data is being placed on the data bus. Accordingly, the status register contents will be set and the flag register will be set to 1. Initially it was 0. So, the third step we will be setting the status register actually. Then after setting the status register, the data accepted will be sent through interface to IO, so that any another IO device or the same IO device should not start sending the next data. Then now the communication between this interface and this CPU will start. From the content of data register that has come from data bus, they will be sent to CPU by data bus, and accordingly input output read or write whatever operation is required will be done by telling the address through address bus. So, now is the communication between this processor and this interface is taking place to handle 1 byte of data transfer. So, in this manner, after the 1 byte of data transfer is complete, this data accepted signal it will be invalidated, so that the IO device can send the next byte of data. That is, in this case, the IO devices, they do not have the direct access to the memory. We can see this, the transfer from IO device to memory, it requires the execution of several instructions by the CPU. As I told ki they are sending the data to the CPU and then CPU is communicating to memory here. So, it will be sending the data to memory via processor. So, the transfer of IO device to memory, it requires the continuous execution of several instructions that are written in the form of instruction program by the CPU. So, an input instruction to transfer the data from the device to the CPU, and the second one is the store instruction to transfer the data from CPU to memory. So, these two types of communications they are taking place. One is our input instruction and the second one is our store instruction. Then, as I earlier told, this is my input instruction to transfer the data from the device to CPU, and this is my store instruction to transfer the data from the CPU to memory. So, in this case, in both ways communication is taking place. So, the device transfers the bytes of data, and we have shown the example for 1 byte of data. So, in this manner all the bytes of data will be sent, and CPU we can see it will be busy always for for communicating between our input output devices and memory. So, the device they transfer the bytes of data one at a time as they are available. So, whenever a byte of data it is available, the device it places it in the IO bus. The first step, it places the content on the IO bus and it enables its data valid line, second. Then after that the interface it accepts the byte and it places into the data register and it enables the data accepted line, as I told in the diagram. So the interface now it sets a bit in the status register and we will set our F4 flag as 1. Then this device it can now disable its data valid line, so that the next data shouldn't come from device to interface, because now from interface to CPU the data will be sent, but it will not transfer another byte until the data accepted line is disabled by the interface. So, in this manner the communication between IO and interface using interface and CPU is taking place, and then from CPU to memory is taking place. That is not shown in this diagram. Then, as I told, the program is written for the computer to check the flag in the status register to determine whether the byte has been placed in the data register by the IO device or no. So, if it is placed, then we will be sending the next byte. That is, it is done by reading the content of status register into the CPU register and checking the value of flag bit. So either that flag bit will be 0 or it will be 1. So if this flag bit it is equal to 1, what does this mean? This means the CPU it reads the data from the data register. Means the transfer is taking place. Whatever data was being typed or communicated through IO device to interface, now from interface to CPU that data is being read. Then, so after the data is being read, that flag is set to 0 for transferring the next byte of data. That is, this flag byte is then cleared to 0 by either our CPU or the interface. It depends how the interface circuits are designed. Designing of the circuits of our control unit, that we have discussed earlier also in our unit 3, that was either through hardwired or through control unit, microprogrammed. That is, once this flag it is cleared, so the interface it will disable the data accepted line, and now the device can transfer the next data byte. So in this manner the data transfer in terms of byte will happen, byte by byte the data transfer for the whole set of data controlled by an instruction program will happen. So we can see these steps. The first thing, the CPU it requests an IO operation. As I told you, CPU is now controlling the IO operations. An instruction program is being written to handle all the set of instructions, IO instructions. Then IO module it performs the operations. Then the task IO module now it sets the status bits. Now the task of CPU it is continuously checking the status bit periodically. If this is cleared to 0, that means that 1 byte of transfer has been taken place successfully, and if this flag is 1, that means the data has to be read from interface to by the CPU now. Then, so IO module it does not inform the CPU directly. Either through interface it will tell. So the IO module it will not interrupt the CPU in this case, and as I said this line, that means ki CPU it has to wait or it will come back later. So CPU is unnecessarily busy without doing anything. It is just waiting and watching ki whenever the data transfer has to take place, whenever the data transfer has taken place or is taking place, just this. So the under programmed IO, the data transfer is very like the memory access. Means my IO device it wants to do the memory transfer and it wants the CPU cycles. It wants the CPU as an observer. So each device it is given a unique identifier because there are so many devices. So every device it will be having a unique identifier, and every device it wants to send, it wants to write into memory or it wants to read from memory. CPU it commands certain addresses. So the steps of instructions execution they are here being shown. The first step, the CPU and IO communication is taking place. We can see that is it issues the read command to the IO module. That is our first step. Then it issues read the status of IO module. That is, now the communication between IO and CPU is taking place. Then third, I am just checking, I means CPU is just checking the status bit. So if there is an error condition, it will handle that, and if the status is okay, that is it will read the word from IO module now. Whatever contents was placed in the data register, in the data bus, now the content of data register they will be placed, they will be sent to CPU via data bus. Then after sending the data to processor, the next task comes, the memory comes into the picture. That is, now CPU to memory communication is taking place. That is, we have to write the word into memory or we have to read from memory. So, then this is the transfer of 1 byte. So, if it is done, yes, the next instruction will be executed. If it is no, then CPU and memory communication for the 1 byte is continuously taking place. So, I can say in this programmed IO method, CPU is staying in a program loop until IO unit it indicates that it is ready for next transfer. So, we can say that it is very time consuming process and it is keeping my CPU needlessly busy. So, what should be next step? It should be avoided. Yes, it should be avoided using an interrupt facility. What is that and how it is that we are going to discuss for our second mode of transfer. That is, we are using some special commands to inform the interface so that it should issue an interrupt request signal whenever the data is available from the device. As we have said, CPU is an electronic device, it is using everything very fast manner and all the devices, various devices, they are very much slow. So, whenever a device wants to communicate to any to memory or CPU, it should send an interrupt request. So, in the meanwhile, CPU should execute some another program rather than wasting its cycle. So, it will increase CPU efficiency. That is, in the meantime, the CPU can proceed for the executing the another program, and the interface, the interface will keep monitoring the device. So, when the device, it determines that the device is ready for the data transfer, it will send an interrupt signal, to the CPU asking for a request. Now, I want some CPU cycle, please give me. So, upon detecting that external interrupt signal, the CPU, it momentarily stops whatever task it is doing and now it branches to the service program to switch over that IO transfer, and after that IO transfer is being completed, it automatically returns back to the task whatever it was performing earlier. So, let us discuss now the applications of this method, programmed IO. As I said, this programmed IO, it is useful in small, low-speed computer. Very beginner cases we have initiated with this method, that is programmed IO. And then it is being used in the system that are dedicated to monitor a device continuously. Let us come to discuss the advantages of this programmed IO. That is, advantages are, it is very simple to implement. The beginners, they started with the programmed IO. Then we require very little hardware support by this programmed IO method. Then next is disadvantages. As we have seen, the CPU is continuously wasting its cycles. It is just waiting and watching. The actual speed of the actual work or the actual efficiency of the CPU, it is not coming into the picture. That is, the processor has to wait for a long time for the IO module. It has to work according to the IO module speed. So, that is of the concern. So, it should be ready for the reception or transmission of data. It is being handled or it is being done when the IO module is ready, and IO module speed is very slow. So, that's the reason the processor also becomes very slow, and we don't want that. So, that is the drawback of this method. Then the performance of the entire system, it gets degraded. Now, move on to the second method, that is our interrupt initiated IO. Interrupt initiated IO, as the name suggests, interrupts are being initiated whenever there is an IO transfer has to take place. Whenever an IO device is being ready for doing the data transfer, it will send an interrupt. So, rather than continuously monitoring of CPU, the interface should inform now. Interface should become the monitor now. It should be monitoring. and it should issue an interrupt request signal IRT. We will discuss through diagram in the next slide for the data availability using some special commands. So in the meanwhile, CPU it should proceeds to execute another program, and the interface it keeps monitoring the device. So whenever we are executing any simple program of in C, let us take the example of addition, subtraction. So if we are implementing in C, and when we execute it, it takes very less time. So in the data structure, suppose we write the program of sorting, then then when we are studying the operating system and we come to discuss the how much execution time the program is taking place for 8 merge sort of using 8 numbers or like that. So we observe that this execution time should be less. So how CPU is when the entire program it is residing inside the main memory, then it requests the CPU ki I want to execute all these instructions. So that execution time is, it should be very less, means CPU is granted entirely to that program for that specific period of time. So whenever those instructions they are residing inside the main memory, then it gets the CPU and all the instructions they get executed. So suppose in that program there is some branching, means there is some go to statement written, or there are some external interrupts if there come, or there are some IO instructions written in or out. In that case, rather than just getting executed sequentially, the CPU the addresses they gets the branching, means the program counter rather than getting incrementing only, it gets it stores its present value and it goes to the next instruction address as per the instruction given in the CPU. If it is in, then the communication between IO device and CPU it starts. That means upon detecting the external interrupt signal, the CPU by storing the return address from the program counter into the memory stack, this memory stack we have discussed it, because they are just a temporary registers, we can say, for storing the temporary values of the program counter, where the CPU has to return back after executing its present now next ready instructions. So then the control branches to the service routine that processes the required IO transfer. Then there are two methods for doing this. One is our using non-vectored interrupt and second is our vectored interrupt. Non-vectored interrupt, the branch address is assigned to a fixed location inside the memory, and in vectored interrupt the source will tell about the branching, means it supplies the branch information to the computer, and this address it is called the interrupt vector. This interrupt vector is nothing, it is just the first address of the IO service routine, or it tells us the address that points to the location in the memory for beginning address of the service routine. Then priority interrupt. If there are so many devices they wants to interrupt to the CPU, to whom it should be given, so that becomes the priority interrupt. So the priority interrupt, it is a system that establishes a priority over the various sources to determine which condition to be serviced first when there are two or more requests they are occurring simultaneously. So high speed data transfer devices such as magnetic disk, they are given priority, and the low devices they are given slow devices they are given low priority. So if two devices they interrupt the CPU at the same time, then the CPU it services the device that has the higher priority. Then how this priority establishment is done? It can be done using two ways, by either software or by either hardware. So the polling procedure it decides it is used to identify the highest priority source by the software means. That is, there is one common branch address for all the interrupts, and the program that takes care of the interrupts, it begins the branch address and it polls the interrupt service in sequence. Then if we are doing the priority using hardware method, then the device with the highest priority, that is using serial manner, then it is called the daisy chaining priority, and the device with highest priority, it is placed in the first position. This is highest priority, then the second priority, then third priority, and so on. So followed by the devices with the lower priority, and that is placed in the last chain. The interrupt it request line, it is common to all the devices. This is my interrupt request that is common for all the devices. Whichever devices they want to interrupt, they want CPU, they will place their address on this bus. Then the CPU, it will send an acknowledgement using this. Whichever devices they have interrupted, so it will set its PI as 1. Suppose this device it wants CPU, so it will set its out value as 0, so that the next device is not able to get the CPU. And when it has placed PI as 1 and PO as 0, then it will place its vector address on this bus and it will place the data on this bus, and in this manner the communication will take place. So the advantage of this is all the devices whenever they want the CPU, they get as per their priority. Then the second method, that was the devices were connected serial manner. Now the devices, they are connected in a parallel manner. This is the devices, disk, printer, reader, keyboard. As per their priority, they are being assigned the numbers, and this is our mask register. It is same as the number of devices being attached, being ANDed together and being given to priority encoder. The output of priority encoder is the vector address that is given to CPU, and the output is given to IST, and then IST ANDed with IEN, it sends the interrupt to CPU, and the acknowledgement to CPU, it is the AND of my IEN and IST, and it enables my vector address that is being sent to CPU. That is the parallel priority interrupt method. It uses a register whose bits are set separately by the interrupt signal from the device. Then the priority, it is established according to the position of the bits in the register, and the circuit it may include a mask register whose purpose is to control the status of each interrupt request. So in addition to this interrupt register, the circuit has mask register that is used to control the status of every interrupted request. And this mask register, it can be programmed to disable the low priority interrupts. Then it can also be, there should be a facility that high priority device to interrupt the CPU while a low priority device is being serviced. So it consists of an interrupt register whose individual bits, they are being set by the external conditions and they are cleared by the program instructions. And the magnetic disk, as we have said, it is a high speed service device. It is given a higher priority, and the mask register, it has the same number of bits as there are number of bits in our interrupt register. So this was all about the first and second method, that is programmed IO and interrupt initiated IO method of modes of transfer. In the next lecture series, we will be discussing about the DMA, that is direct memory access. Thank you.